Have you ever stopped to wonder about the hidden language that's powering pretty much everything in our modern world? I'm talking about the graphics in video games, the algorithms that run the economy. Underneath it all, there's this really elegant mathematical structure. So, today, let's pull back the curtain and decode the basics of matrices and vectors. I mean, really think about that for a second. How on earth does a computer handle the insane complexity of, say, spinning a character around in a 3D world? Or how does a streaming service sift through millions of movies to say, hey, you'll probably like this one? It feels like magic, doesn't it? Well, it turns out the secret isn't magic at all. It's actually way simpler and honestly way cooler. It all comes down to just organizing numbers into a simple grid. That's it. This humble grid of numbers is the fundamental building block for so much of the tech that we literally use every single day. All right, so here's how we're going to break it all down. First, we'll figure out what this information grid actually is. Then, we'll learn the basic moves, how to work with them. After that, we hit the big aha moment and see how they solve huge problems. We'll find a magic number that unlocks their secrets. And finally, we'll see how these grids can literally become arrows that point the way in space.
Okay, first things first. Let's start right at the beginning. What exactly is this grid of numbers we keep talking about?
The fancy math term for it is a matrix. Now, the textbook definition is a rectangular array of numbers, but honestly, forget that for a second. The easiest way to think about it is just to picture a spreadsheet or maybe even a chessboard. It's just a box, a container for holding information in a super organized way.
And here's the most important rule of the road. The flat, horizontal lines of numbers are called rows. The upright, vertical ones are columns. And here's the key. You always describe the size by its rows first, then its columns. So a matrix with 2 rows and 3 columns is a 2 by 3 matrix. It's a simple little detail, but it's absolutely crucial.
Now, not all matrices are created equal. They come in a few different flavors. You've got your row matrix, which is just one single row, and your column matrix, which is one single column. Pretty self-explanatory. If the rows and columns are the same, we call it a square matrix. Then there are a couple of special players. The zero matrix, no surprises there, it's full of zeros, and the identity matrix. That's a square one with a clean line of ones running down the diagonal. Keep that one in the back of your mind. Trust me, it's a VIP.
Okay, so we've met the players. Now let's see how they actually play the game. It's time to open up the toolkit and get our hands dirty with the basic rules for what you can do with matrices.
And here's the good news. The easy stuff is, well, it's really easy. If you want to add or subtract 2 matrices, they just have to be the exact same size. Then you just match up the spots and add or subtract. Done. And if you want to multiply a whole matrix by just one number, we call that a scalar. You just multiply every single little number inside by that one number. It's that straightforward.
But then there's multiplication, and this is where things get a little spicy. There is one golden rule, a non-negotiable rule you can never break. To multiply matrix A by matrix B, the number of columns in A has to match the number of rows in B. If they don't match, nope, can't do it. The math just doesn't work.
So how does it actually work? It's kind of like a little dance. To get the number for just the top left corner of your answer, you take the entire first row from the first matrix and you match it up with the entire first column of the second one. You multiply the first numbers together, the second numbers together, and so on. Then you add all those little products up. That one final number is what goes in that top left spot. Then you just repeat that row by column dance for every single other position.
All right, I know what you might be thinking. This is a lot of rules, a lot of math. So what's the point of all this? Well, get ready, because this is the payoff. This is the aha moment, where you see why this is all so powerful.
So check this out. On the left, you've got this messy jumble of equations. Remember these from algebra class? A total headache. Now, look to the right. It's the exact same information, but wow. It's clean, it's compact, it's just one simple equation, ax equals b. All that chaos bundled up into one beautiful, tidy package.
And the best part about getting it into this neat form? We have a systematic recipe for solving it. Using a method with a fancy name, Gaussian elimination, we can do simple, legal moves like swapping rows or adding rows together. It's basically a super organized way of cleaning up the puzzle until, boom, the solution for x, y, and z just appears, clear as day.
Okay, now for a little bit of matrix magic. It turns out that square matrices have a secret number hidden inside them, a special value that tells us some really important things about them. This leads us to determinants and inverses.
This magic number is called the determinant, and you can honestly think of it like a matrix's unique fingerprint, or its ID number. It's just a single number that you calculate from the matrix, but it packs a punch. It encodes some crucial information about that matrix's personality.
So why do we care about this fingerprint number? Well, here's the single most important reason. If that determinant is anything other than 0, it means our matrix has an inverse, and an inverse is, for all practical purposes, an undo button. And having an undo button, that's a total game changer for solving those big AX equals B problems we were just looking at.
All right, we're on the home stretch now. We've seen how matrices are amazing for organizing data in a box, but what if we use them to point the way? That's where vectors come into the picture.
Think about it. All the numbers we've talked about so far are just kind of sitting there in the grid, right? They're static values. But in the real world, things move. Things have a speed and a direction. How do you possibly capture something like the force of wind or a character running across a screen in a grid of numbers?
Well, the answer is a vector. And get this, a vector is just a skinny matrix. That's the big connection. It's a matrix that only has one single column or one single row. And all of a sudden, the numbers inside aren't just values anymore. They're coordinates. They're the instructions for drawing an arrow in space.
And this is what is so incredibly cool. The math we do with them becomes visual. When you add two vectors, for instance, you're literally just following one arrow from start to finish, and then picking up where you left off and following the second arrow. The answer is just the shortcut, the one arrow that takes you directly from your original start to your final destination. It's pure visual logic.
Okay, so let's tie this all together. What are the big takeaways? 1, matrices are basically super spreadsheets for organizing huge amounts of data. 2, we can do math with them to systematically change that data. 3, their biggest superpower is taking messy, complicated equations and making them simple to solve. And 4, vectors are just a special type of matrix that acts like an arrow, giving us both direction and length.
You know, it really brings to mind that famous quote from Galileo, "The book of nature is written in the language of mathematics." And what we've seen today is that these things, matrices and vectors, they're not just problems in a textbook. They are a huge part of that language. They are the code running underneath so much of our world.
So the main thing to remember is that these simple grids of numbers are like the Lego bricks for building unbelievably complex and powerful systems. And honestly, we've only just scratched the surface here. Which leaves you with one final thought. Now that you know to look for them, what other hidden structures, what other mathematical languages are all around us right now, quietly shaping our reality?